Awesome. Our last session preview this morning is Sasa Misailovic on automatic differentiation.
All right. Hello, everyone. So this is the set of slides for automatic differentiation session. Some of those slides I borrowed from my student, Jacob Laurel. And I'll tell you about the technique that is now being popular in various domains, including machine learning, optimization, probabilistic programming, robotics, graphical art, scientific modeling. It's been having a resurgence in machine learning. That's why we also have it in programming languages. But differentiation has been a long time topic in scientific models. What is it all about? Well, the whole goal of automatic differentiation and differentiable programming in general is to say the following. We have some computation, let's say this function that computes a square, and instead of just producing a value, we want to produce both the value and the derivative at the same time. So the computation now has two parts. And we hope that we can get the second part automatically. How do we have the formula for this second part? Well, this is the good old dy is 2 times x dx, right? And in general, how would we come up with rules for arbitrary computation? Well, we go back to the good old calculus books. And this is the flavor of the talk today. Now, for most programmers, we want to hide all the intricate details of calculus, and this is exactly what the tools help us do. And there has been a big swath of tools that can help us produce derivatives automatically, including PyTorch, JAX, TensorFlow, Piano, and so on. So why do these computations are necessary? Well, they can speed up and enable us to do correctly various tasks. One of them, it's most familiar by now, is neural network training, because here are derivatives here. Here's the gradient, and you need to compute it in neural network training to determine which of the weights of the network contribute most to the loss when you train it on a set of inputs. Other example where they are necessary is, for example, when you have analysis of robustness. So you say, hey, there is a complex decision boundary. Should I stop or go? And depending on what angle you took the picture, you may be a different place in this space. And gradients can help you bound the slope and tell you whether you will ever cross the decision boundary. All right. So this is motivation. Now, where do we go from there? We go back to the books. Quick reminder, what's derivative? You have a function that takes a single input. Well, derivative is telling you how much, when you change the input by a little, how much would the output change. And the slope of this line is describing the derivative. Calculus 1, right? Now, we want more complicated functions. Function with multiple inputs. We just progress from single derivative to partial derivatives and to gradients. And gradient is just a vector of partial derivatives. Visually, what would that be? That would be a bunch of those. That would give you the coordinates of all of those little vectors that tell you the change in each direction. Next step, we want more complicated functions. So now we have functions that return vectors, or we can express it this way. So multiple inputs, multiple outputs, and we go from gradient to a Jacobian. So what is Jacobian? It's just a matrix with all partial derivatives for all function components. Okay, so we kind of have the basics of the background here. And then for automatic differentiation, there is one more rule that's almost dominating the discussion. And that is, we know now for the individual steps what to do. How do we combine it together? Well, that's the role of the chain rule. And the chain rule is telling us if we have a composition of functions, like f of g of x, how do we compute the derivatives in this case? And in the case of computation, that would be you have one statement, another statement, third statement, so on. Well, again, the rule from the textbook would say, well, come up with some intermediate variables, and then the chain rule can go this way. Derivative of z with respect to x is derivative of z with respect to y times derivative of y with respect to x. Or if you want it in another notation, it can be expressed this way. Again, calculus 1. How do we extend it to calculus 2, multiple variables? Well, we need to think about two things. One is, does a decomposition like this cause some dependencies? So making it a graph of dependencies. And second is, when we have multiple variables, how do we go about that? Well, the answer is, we are just, instead of multiplying individual values, we're multiplying Jacobians and summing up over different dependency paths. All right, so why is this important for us? Well, remember a neural network. What is a neural network but just a composition of different functions that you apply on input vectors? So computationally, what we want to accomplish is that at the same time, we compute both the values after each layer and we compute the derivatives. And there are various directions in which you can do it. Two dominant ones in machine learning are going forward or reverse. And each one would have its pros and cons. So forward mode AD is simple to implement. It works well when we have only a few inputs and reasonably it has reasonable memory footprint. But the big problem is it doesn't compute gradient right away, but you need to do n computations to compute the gradient in the horizontal direction. It's good for something like a robust analysis when you have one angle and you want to do sensitivity towards it. Reverse mode, well, that one is more complicated, but the reward is you can compute gradient right away. But you need to do two passes. First, you need to find dependencies, and then you need to try to find a way how to push the computation of the gradient from the output towards the inputs. That also requires additional memory, and there is a lot of work on how to optimize it. And that's where the talks are going to go today. So here is that's where we go in training. One trick, and something where the papers help us is, so here's one technical detail. Dual numbers. We all know complex numbers, right? Well, dual numbers are similar. It's just we have this special number, epsilon, that's by itself not equal to 0, but epsilon squared is 0. And that allows us to compute gradients nicely. We can first do arithmetic just like what you would do with ordinary complex numbers. But fun fact, and that's something that's, that we can use, is that, well, if you do Taylor series for this computation, what happens? Well, epsilon squared is 0, right? Epsilon cubed is epsilon squared times epsilon. So all these terms are zeroed out. And what you end up with is that f of a plus b epsilon of one of those dual numbers is just f of a plus f prime a b. And this way, we can simulate chain rule and have the propagation of the numbers. Implementation, simple. And let me then go into today's papers, where I'll just tell you that they try to resolve various computation challenges, both on the semantic level, on the level of transformation, and the level of static analysis. First paper is telling us how to get both reverse and forward AD implementations from the same starting point, and identifies the conditions and the set of transformations you can apply to get both of those implementations derived together. The second paper is showing us how we can use the strength of dual numbers in reverse mode automatic differentiation, and how to optimize it to actually be competitive with other reverse AD algorithms. And the final paper is showing us how we can extend the forward mode AD and how to be careful about it to apply to probabilistic programs, where you also need to think about expectations and other aspects that are not present and in just general AD software. So why to go to this session? Well, it's a nice intersection of continuous math and PL theory implementation. And It's a nice starting point of thinking about all of these problems together. So 510, so 1625. Great. Baldrum A. See you there.